now. Is this better? That is better. Okay, wonderful. So hi, everybody. I'm Ronan Kerr, currently soon to graduate grad student at UT Austin, but soon to be going on to a Dunlap Fellowship at the University of Toronto. I'm going to be discussing my continuing work on the Spyglass program. And this is fundamentally a project to use young stellar populations to learn about the process of star formation. This worked when I tested it. Why isn't it working now? So young associations are great for learning about the star formation process because of the fact that even though there's a lot of very fascinating physics that happens in the gas phase, once that gas disperses due to the feedback from the stars, that gas loses its ability to record the history of that region. And instead, it's the stars that have an imprint of the dynamics and the ages that formed them that can provide this beautiful record that lasts for a very long period of time and can trace tens of millions of years of a star formation history. And this can tell us things about how processes like stellar feedback, galactic dynamics, turbulence, all these different processes work together to trigger and sustain the process of star formation. And how do we do this? Well, first thing we need to do is identify young stars. We use a Bayesian framework to do that by applying that to Gaia photometry and astrometry. And we identify these two regions on the premium sequence and the tip of the ONB branch to identify stars as reliably young. And we use these stars with fundamentally young Gaia luminosities around the solar system, which is where the acronym comes from, to identify young stellar populations. We cluster using HDB scan, and we produce these beautiful maps. This is a top-down view from the top of the galaxy down onto the sun of the distribution of young stellar populations within 333 parsecs. This is from my first paper. And then I recently expanded this to kiloparsec in Spyglass 4, revealing 116 groups, 10 of which are completely new, and 20 have no direct literature equivalent. So this work is already pushing the boundaries of our known young stellar populations up to and beyond the limits of those that have been previously known. And there are a few things to note in this result. So first of all, we have the emergence of some features on very, very large scales, such as the Cepheus-Hercules complex, which we're going to discuss a little bit later in this talk. Got a lot to say about that one. But we also have some interesting connections emerging between well-established populations, for example, between Perseus and Orion, which are fairly far apart on sky. But it turns out that when you do this sort of fine clustering, you see that there's actually low-density populations with very similar velocities that essentially bridge the gap between Perseus and Orion and have very similar ages as well. So not to say that those are definitely connected populations, but it's an interesting feature that's worth looking into further. And yeah, that really doesn't work. I should stop trying to do that. So on smaller scales, we also have some interesting features emerging. For example, a group of small populations that have a combination of high transverse velocities and positions that can be upwards of 200 parsecs above or below the galactic plane. And this is very odd for a young population because they tend to be more or less solar motions and positions very close to the galactic plane. So we're interpreting these as potentially the product of infalling gas parcels infalling from high up in the galactic plane towards the material in the plane and potentially causing star formation through that interaction. But bottom line through all this work is that we're getting all these new environments where we can decode star formation histories. And what we can do is we can do regional studies. And the goal of these is to reconstruct the star formation history of a region. So what we do is we identify a group of stars that has confirmed membership. We substructure it to basically break the population down into its most basic components. These most basic components are the populations where we're most confident that they formed at the same time in the same cloud. Within those populations, we can compute ages using a variety of different methods. We can then take their locations from Gaia, and we can take their velocities from a combination of Gaia and supplemental radial velocities and trace them back from the present day to their location at formation. And through that, you can reconstruct the entire history of a star forming event. So what you're about to see is going to be a video of, not a simulation, just the locations of stars, traced back in time, and then we're going to trace them back to the present day, letting them pop in as they form. So this is the result in two associations, All-Star Complex on the left and Cepheus Far North on the right. And what you'll probably notice initially is that we actually have the emergence of two of what we're calling nodes in each. So we have Takhor here, and we've got Fornix, Rologium, Carina, and Columba that are all going to form more or less co-spatially in the All-Star Complex. And we have Beta Cephei here and E Draconis here in Cepheus far north. So even though these populations in the present day, which is about to take place in both of these videos, they are very contiguous. When you trace them back in time, you reveal substructure. And what's interesting is that this substructure is often not consistent with what you see in the present day. So we did a preliminary clustering analysis in Cepheus far north at the top here. And what you'll notice is that the only population that was notably separate from the rest in this analysis was actually Beta Cephei. And Beta Cephei is in purple here, notably not its own node. So this is to say that it appears as if this sort of traceback analysis might be necessary to uncover these sort of primordial structures in these associations. And another thing to note is that we seem to be seeing a sort of blurring of the definition of what is an association or a population on larger scales. So I want you to keep your eye on this little blue group right here, which is Platée 8. This group is normally associated with clusters in the vicinity of SCO-SEN, for example, IC2602. And what we find in our work is that it stays near the Austral complex through most of its existence. It forms at about the same time. So it would be weird to consider Tuck-Core part of this population and not Platée 8. And that sort of opens up a bridge to these populations around SCO-SEN. So we start to realize that when we go to large enough scales, we keep seeing structure all the way up. So it might not be good enough to just do these regional studies on individual populations. We might have to expand to larger scales to really fully understand what's going on. And so just to briefly summarize this regional traceback part of the talk. So we're getting this emergence of nodes as a very useful unit of star formation, representing the semi-continuous co-spatial star forming events that can last for nearly 10 million years each. And we appear to need traceback to identify them. They do not readily emerge through clustering alone. And we also see that star formation is interconnected. Current configurations can be misleading, and association boundaries can blur on large scales. And as a result, we need a sort of larger regional context to fully understand what's happening in a given star forming event. So my first foray into doing this in sort of like larger scales is my work on the Cepher complex. And this is really an underappreciated population. It's within about 250 to 400 parsecs. With about 200 O and B stars, which automatically makes it larger than SCO-SEN on the O and B metric alone. And I recently submitted a census paper that revealed that there's actually 2 RV components in this population. And each of those RV components actually has 2 components in age as well. So for a total of 4 stellar structures. And 3 of these component structures have extensive substructure themselves. And these are Orpheus, Cineris, and Cupavo. And in Orpheus, we have a very large population containing about 10,000 members and including 2 open clusters, making it one of the largest associations within 500 parsecs with a fairly substantial age spread, as well as 2 confirmed planets. If you want to learn more about that, I suggest that you talk to Luc Bauma over here. And we also see the emergence of 3 expansion origins in this figure here. So we've got low velocities here, low velocities here, and low velocities here, but then we see expansion around each one. So this could suggest that there are more nodes to be uncovered in the velocity field of this association. So that's something we want to explore very soon. And in the Cineris association, which is a little bit smaller, similar age spread, also has 2 confirmed planets, we see the emergence of an age gradient going from 36 million years in RSG5 all the way down to 30 million years in the smaller population of Cineris 6. And you can see the very nice, very clean trend in the velocity spread here. And we're interpreting that as what's referred to as sequential star formation, which is where an initial burst of star formation compresses adjacent gas, which causes more star formation, which compresses adjacent gas, and so on, until you essentially consume the entire cloud. So we have some interesting features emerging in both these populations that are worthy of the sort of association level traceback that I've already done in CFN and in the Austral complex. However, I want to take a second here before I finish to sort of expand a little bit and just see what happens if you don't worry about the fact that there's component associations in Cepher and just look at all of it together. And when you do that, some interesting things begin to emerge. So let this cycle back through. What you'll see is that the initial burst of star formation, so galactic center is locked to the right here, so we're co-rotating with the galaxy. The initial burst of star formation in Cupavo happens aligned with a typical spiral arm pitch. And then as those stars get close to what's about to be Orpheus, we see a major burst of star formation that potentially could be triggered by that initial event. So even though these populations don't appear to have a lot of direct connections in their origins, when you zoom out to larger scales, you start seeing these connections. As a result, it's a priority of mine in the future to continue regional studies and continue to flesh out this view, because on the sort of scales that these populations existed at formation, we're seeing like 600 parsecs on each edge here. You just know that there are other populations that are interacting with all of this that are not present here that we need to know about if we want to really understand how these populations form. So with that, I'll give up my time, and people can feel free to ask questions to me. Thank you. First conclusions.
So wonderful presentation, very large cluster structures. I'm wondering if you've been able to look at the data to try to understand the triggering mechanism that might make these clusters related, supernova, gas compression, however they may be communicating with each other.
Yeah, so I think that's a big thing that we're trying to figure out, is exactly what those mechanisms could be. And they can be difficult to disentangle at times, especially between things like, stellar feedback and supernovae, which have very similar expressions in the stellar record. But one thing that we probably can disentangle, if we have enough information, is between something like stellar feedback and, for example, compression through like galactic structure and evolution like that. So if we see the emergence of sort of patterns on larger galactic scales, and we see sort of bursts of star formation along those patterns, we can sort of say that this is galactic structure driven rather than driven by a cluster of supernovae or something like that. And that sort of like speaks to the importance of having this sort of like larger context when we're doing these sort of assessments. Yeah.
Really nice talk, thank you.
Thank you.
You mentioned that if you need tracebacks to identify substructure in some of the manifestations, I'm assuming that given they're very young, it's pretty linear and there's not much curvature from the galactic type.
Yes.
How then is it not possible to identify them directly in XYZ BW, these substructures?
Yeah, so I thought I'd just quickly note that we are tracing back through the galactic potential. So that is being considered. Now, there probably is a way to do it. Now, that's something that I'm sort of pondering myself. When you just do it like simply with like HDB scan clustering, it's very easy to not get the structures that you expect. So it's sort of the kind of thing where I've been pondering just getting a sample of like well-defined structures at formation. And once you have that sample of, convincing structures, you can start doing the like reverse engineering. It's like, okay, what exactly do these things look like? How do we get them out of just the space velocity distribution? However, it is worth noting that we do have instances like Cepher, where they are basically right on top of each other in 5D space velocity coordinates. And in RV, they are way apart. So you can get some really weird aliasing. So you got to be careful.
Thank you very much.
I did that wrong. There it is. Good. Thank you.
Thank you. Can you hear me back there? Oh, great. Thank you. My